When two objects interact against each other and exert an external force on each other, action and reaction, the momentum of each object changes after collision, but the total momentum of the two objects remains the same. The total linear momentum of an isolated system remains constant in both magnitude and direction. This is known as principle of conservation of momentum. Let us see as to whether we can prove this by considering an example. A bullet of mass small m is fired from a cannon of mass capital M. Once the bullet is fired, the bullet leaves the cannon at a tremendous velocity, say v. At the same time, the cannon too moves a little in the opposite direction with a velocity, say v. If the force exerted by the cannon on the bullet is F, then, according to third law of motion, the bullet exerts a force of minus F on the cannon. Let the two forces act in a time interval of delta t. Before firing, the cannon and the bullet are at rest. Therefore, their initial velocities and momentums are zero. That is, total momentum of the system, cannon and bullet, equals zero. Immediately after firing, the bullet leaves the cannon in one direction and the cannon recoils in an opposite direction with a momentum which is equal and opposite to that of the bullet. If Pb and Pc are the momentums of the bullet and the cannon, respectively, after firing, Pb equals minus Pc, as these are in opposite directions. That is, Pb plus Pc equals zero. That is, the total linear momentum of an isolated system remains constant in both magnitude and direction. If there is no external force from outside a system, as in the above example, though each particle exerts an external force on other particle causing momentum on each other, the momenta cancel out, as they are equal and opposite. The total momentum is conserved. This is what is stated as law of conservation of momentum. The total momentum of an isolated system of interacting particles is conserved. An important application of the law of conservation of momentum is in collision of objects, an example of which we will see now. Let two trolleys A and B with initial momenta PA and PB collide against each other and get away with momenta P-A and P-B, respectively. If the time duration of the collision is delta t, according to second law, their impulses on each other are FAB delta t equals P-A minus PA and FBA delta t equals P-B minus PB. Since FAB equals minus FBA by the third law, P-A minus PA equals minus P-B minus PB. That is, P-A plus P-B equals PA plus PB. This shows that the total momentum of the two trolleys after the collision is equal to their total momentum before the collision. This holds true in the case of both elastic and inelastic collisions. Elastic collisions satisfy another condition also. Total initial kinetic energy of the system is equal to the total final kinetic energy.